Good morning, everyone, and welcome to Autodesk Virtual Academy, brought to you by Cative Technologies. I'm Nigel, and I'm Customer Success Manager here at Cative Technologies, and I'm joined by Nikhil Venkat. How's it going, Nikhil?
Pretty good. How are you, Nigel?
Good. So Nikhil is one of our simulation experts here on the team. He has a lot of experience in FEA analyses, even doing hand calculations, which are my least favorite thing in the world. I do love my quadruple integrals. So today we're going to be going over something really cool in Nastran In-CAD, and that's stress linearization. And don't worry if you don't know what that is. Nikhil will explain that for you. I know he had to explain it to me for me to find out what it was. So it's something new that was in a recent addition to In-CAD, which is the 2019.1 release, if I remember correctly. And we want to make sure that everyone's aware of what's available in the tools, and that's part of why we do Autodesk Virtual Academy in the first place. So with that, I think my explanation of stress linearization is nowhere close to what it's going to be from Nikhil here. So what I'll do is I'll let him take over from here. But before I do so, if anyone does have any questions, feel free to ask those in the GoToWebinar chat panel. In addition to that, I'm just going to fire a poll here real quick, just to understand what the audience looks like in regards to simulation options. So I'll give everyone a couple of minutes, or not minutes, a couple moments to answer this while I pass it over to Nikhil, so that he can explain what stress linearization is. So Nikhil, take it away.
Thanks, Nigel. Nikhil, by the way.
Yeah.
So as Nigel mentioned, today we're going to be talking about stress linearization. It's something that was just added into Nastran In-CAD in the 2019.1 release. So we want to go over some basic things about what is stress linearization, why is it important, how do we essentially do stress linearization, how do we linearize stresses, how do we get the results that we would expect, and then we'll go over some questions which hopefully we can provide answers immediately. So first of all, stress linearization is something that you will see available in the Nastran In-CAD 2019.1 release, which was the most recent one, the most recent update. It released in July of this year, a couple of months ago. So in case if you have installed the update, then you will see a giant stress linearization button right in the middle of your results panel. You should not miss that. So in case you haven't installed it, then you can go into your desktop app, or you can go into your Autodesk portal, and you should be able to find the update there and install it. And if you haven't upgraded to 2019 just yet, then here's the reason to do so. This, by the way, I have to mention, is just one of the things that's new in the 2019.1 release. You have a few other new features as well that make In-CAD much more user-friendly and a lot easier to use now. So I would recommend going and exploring that as well. But the stress linearization, essentially, it is the separation of stresses through an actual thickness into membrane, or into constant membrane stresses or average stresses, and bending stresses, so that the net force and moment across the thickness remains the same as that due to actual stress distribution. It's used typically to comply with design codes and requirements of the pressure vessel industry. You can use the stress linearization utility to graph local stress tensors along a linear path, and/or determine the relative contributions of bending and membrane stress for any kind of structure. The two different methods of determining the membrane and bending stresses, one being based on the maximum shear stress, the other one being based on the von Mises stress, and Nastran In-CAD calculates and displays results based on both methods. It's also worth remembering that while the lion's share of the application is for pressure vessels, it's not limited to pressure vessels. In fact, you can linearize stresses through any structure as long as it makes sense to do so, by which I mean as long as it makes sense to extract separate bending and membrane stresses. Now, stress linearization utility, it graphs, as we mentioned, it graphs the specified stress tensors along what is called a stress classification line. Now, this stress classification line is user defined, and it is a straight line that runs from the inside to the outside of the vessel. FEA provides the raw stress data at nodes along this line. What the stress linearization tool does is it takes the nodal data for this complex stress pattern and breaks it down into components. So those components, as we mentioned already, are membrane stresses, bending stresses, membrane and bending stresses, which is the sum of the two numbers, and the ASME code allows the membrane bending stress to be higher than the membrane stress itself. And also the peak stress. The peak stress is the highest stress found along that stress classification line. This is always positive, but not necessarily higher than the membrane plus bending number. Peak stress is something that you would usually use to determine the fatigue life at the stress classification line. So, excuse me, it's important to remember and understand what each of these stress components, these linearized stress components, refer to and what they're actually doing. Now you see this image on your screen. That just describes the different kinds of stresses. So you have your stress classification line, or the tangential stress, rather the SCL is along the tangential stress line. You have the hoop stress, which is either into or out of the plane, and you have the normal stress, which you can of course determine. Rather, you can determine the hoop stress once you have the normal and tangential stresses using the right-hand rule. Now, why is this important? It is important because linearized stresses is what you have to compare to the standards and the requirements in the ASME boiler and pressure vessel code. So the ASME pressure vessel code is based on the observed safety of vessels. It is a real-world working standard which specify minimum requirements for design, materials, fabrication, and testing of pressure vessels. And the way that this code was developed was almost completely empirical. So its roots were born of failed pressure vessels much before stress concentration was even understood, and the concept of stress concentration was even understood. So at the start of the code, people ran out of theoretical explanations when designs got more complex in simple cylinders and spheres. So when further rules were required for items like flanged and dished heads, they actually built full-sized vessels and models and tested them. And the observations, they did this a number of times, and the observations were then turned into a set of design rules. Vessels did eventually become safer through these efforts. So what it actually gives you, what the ASME pressure code gives you, is a breakdown of primary stresses, secondary stresses, and peak stresses, as we already talked about. Primary stresses are the general membrane stresses, local membrane stresses, and the bending stresses separately. The secondary stresses are an addition of all these, a sum of all these, and the peak stresses, of course, are the highest stresses. Peak stresses are the highest stresses along the SCL, which you would use for fatigue life. You also have sections that are called design by rule or design by formulae. So that's, if you're using these rules directly, if you're using hand calcs, as Nigel mentioned, being his favorite part.
Oh, yeah.
If you're using that, you have separate codes for that. And if you're using FEA, then you have a design by analysis section, which is what we would be interested in. Now, as we mentioned earlier, the ASME boiler and pressure vessel code, just like stress linearization, doesn't just talk about the pressure vessel shell. It also talks about flanges. It talks about welds. It talks about a whole bunch of things. So if that's something that you're interested in, then there's a specific way that you would analyze that. So if you're interested in best practices about welds or anything of that sort, then please feel free to
Call Nikhil.
Yep, contact us, contact Nigel, contact me. One of us will be able to help you. Now, I did mention that a lot of this, a lot of the empirical design rules help make designs safer. Now, that's not an absolute statement, because as recently as 2002, this data is from 2002. This data was taken from the National Board of Boiler and Pressure Vessel Inspectors, their bulletin from summer 2003. As you can see, what's highlighted in red talks about the frequency of faulty design or fabrication. And somewhere in the text, they actually mention that most of this, even the fabrication errors, most of them can be attributed to design errors. So even though we have a set of acceptable standards, there is no silver bullet, I guess, to get a design right. So it's important to understand exactly what you're doing, exactly what you're analyzing, in order to make sure that you don't have faulty designs, you don't have catastrophic failures. And some of these numbers, especially when it involves heat, you look at a total of 100 and something accidents a year, and that's fairly concerning, because that says we're looking at 10 accidents a month on average, which is fairly concerning. This is the last time, by the way, they released a breakdown of data like this. So the hope is that these statistics have improved and we don't have nearly as many failures or errors today. So let's jump into Nastran In-CAD real quick. So can you see my screen?
Yeah, we'll just double check and we're good to go.
Perfect. So this is a simple low-down pressure vessel. So it has 4 legs and it has a bunch of nozzles, pressure head, apologize. Now, to make this easier, we have cut this model in half. That's just to make the analysis quicker and everything. And we're going to be using a symmetric model. So I'm going to jump into Nastran In-CAD here real quick. And so I have some mesh settings set up already. Just going to go and mesh that quickly, if it does.
Cool. And while we're waiting for all of this to run to Nikhil, if anyone has any questions during any of this, or we're going too fast, please let us know, and we'll either slow down, reiterate something. Yeah, so on and so forth.
Okay, so we want to set this up. It's a very simple setup. We're just looking at a simple pressure test on this. So for constraints, I want to fix the 2 legs. I'm also going to cheat a little bit here and fix that edge there. That in truth is not exactly fixed, but it is held in place. Just to make our life easier, we're going to fix that completely. And as we mentioned already, this is a symmetric model, so we have to account for that symmetry. So this is symmetric about the z-axis. It's going to select all of those surfaces, those cut surfaces. So those, that surface there, that one, think that's all of them. Yep, looks like all of them. Now for loads, we don't really care about the flanges. I'm only interested in the shell. I'm going to use a fairly small load, 5 megapascals, which roughly is 750 psi. So I'm just going to analyze the shell itself, and I don't really care about anything else, the flanges or any attachments. We're using steel for this, although, again, I understand general practice is to use something much stronger than steel, so super duplex maybe. But for the sake of this problem, we're just going to use steel. I'm going to go ahead and run the model.
Ooh, and while that's running, it's going to take a little bit to run that guy. Go ahead and ask any questions while we're doing this. We have about 30 seconds to a minute to do so. Stephen asks, you're running this on a part file. Is there any difference or reason why you're running it as a part rather than like an assembly?
Yes. The only thing is simplicity, because if we're running it as an assembly, then we will have to specify contacts between the different mating components, and it adds to complexity, it adds to solve time. So in this case, since we're just doing a quick example, I figured it was easier to just combine the whole thing into one single part, assume that the whole thing is bonded, and run it that way.
Yep. In some cases, obviously, you're going to want to run your analysis on an assembly based on what kind of thing you're trying to solve, right? If there's motion between two components, probably going to want to do that. When it's like things like bolted connections, probably going to want to do that as well. Let's see. Before this is done, another question from Curtis. Why are you applying the pressure to the outside surface and not the inside surfaces? Any particular reason?
No particular reason. Again, we're just looking at the strength of the shell itself. So again, the pressure code I know calls for internal pressure, because again that's what this pressure vessel does. But we're not actually following the code. The idea is to figure out how we can use stress linearization and how we can correlate that with the code. So I suppose it's just more it's just easier visually. It's easier to understand with the compression as opposed to expansion. Okay, so this is what I mean, by the way. You have this giant stress linearization button, which you absolutely cannot miss. So since we fixed this, we have this edge being held down, and the rest of it essentially getting crushed, getting crumpled. I want to make this a little better visually. So turn off. Actually, I'll keep element edges on. Turn off loads and constraints. You can also turn it off in here, by the way. So if you look at our stress results, since we have used solid elements, we have solid normal stresses in different directions, we have shear stresses along different directions, we have principal stresses, but we don't actually have bending and membrane stresses, right? And the von Mises stress doesn't actually give us that information. So we're going to have to linearize the stress. Right, so if I hit the stress linearization button, second, go. So this is the stress linearization dialog. The idea is to define the tangential, the stress classification line, which is along the tangential stress line, and then define either an n-axis, a normal line, or an h-axis, a hoop line, the hoop axis. So for the first point in the stress linearization, I want to pick a point on the inside. You can do this in three ways. You can either enter the coordinates of the point itself, or you can enter the node number if you know it, however unlikely that may be, or you can just select that, make sure your cursor, that box is active, just go in and click, and it's going to automatically capture that node number. The last point, again, keep in mind that this is the SCL, this is the tangential stress line. I'm going to pick a point on there. And now we need, actually, let's pick a point there. Okay. And now we need a normal point. So I'm just going to pick that. So you also have the number of divisions. So if you want a smoother curve, for example, you can increase the number of divisions if that helps you in any way. But now up here you can see the different tensors. So this is the normal tensor, the tangential, hoop, normal and tangential, and so on. This gives you a good idea of what you should be looking at in terms of stresses, because at the end, these are the numbers that you want to be comparing with the pressure code. The PM refers to the principal membrane stress, principal bending, principal membrane plus principal bending. This is based on shear stress, and based on 1 Mises, again, membrane bending, membrane plus bending. So you can also export this to a CSV file. So I'm just going to say pressure vessel data. So if we open that up, you'll see that now we have these results. We have the 1 Mises stress results. We have the shear stress results based on the results that we have in here. It tells you the reference points. The point defines the n-axis, the normal axis, and so on. So this is a convenient CSV file that you can use going forward. Now, you could say, well, I have seen membrane stresses in Nastran In-CAD before. I can use shell elements and get a membrane stress, and that would make total sense. It would make total sense, and you can use a shell element almost through the midplane of this, and assign a thickness to that, and go from there. A couple of issues with that. One being, potentially, you could potentially have certain components that cannot be shelled, or that can be shelled, but don't necessarily make sense to be shelled. So in those cases, you're going to have to connect the shell to the solid elements, which is never ideal. And secondly, the way membrane stresses on a shell element are calculated is very different than membrane stresses extrapolated from solid element results. So you will see some difference in results, and again, that's not really an apples to apples comparison with the pressure code. The entire idea behind this is to make sure that you have that apples to apples comparison. You're always looking at it on the same scale, so you can define your safety factors, etc. So that's the concept of stress linearization. Any questions?
Yeah, so there's definitely a couple of questions, and I think some of these can be answered with some of the previous videos that we've done.
Mm-hmm.
First off, is there a particular recommendation for number of elements, specifically solid elements, in a through thickness direction?
in a through thickness direction. So I'm
assuming like on
I think it's through the thickness here.
Yeah.
You want at least one element. I think most of the time the meshing engine forces you to have at least one element in there. It fails otherwise. So you would want at least one element, but again, it depends on what you're expecting to happen through this thickness, right? If you have some very different behavior from one end to the other, then yes, you do want a large number of elements to capture that. If not, and you're just expecting the behavior to be more uniform, then yes, one or two elements is going to be fine.
Yeah, it really depends, right? When you're looking at like solid structures or whatever, in regards to meshing, any areas of note is what I like to say in the particular model itself. Any areas of note where you're expecting something weird to happen, or you're expecting a very large difference between one side and the other side of a particular surface, you're going to want more elements, right? But for here, we're expecting pretty uniform, deformation and stress across the entire surface. So you don't need to necessarily increase the mesh number for that. But if we were doing something like, like a static bend test on a particular thing, obviously you're going to want more elements depending on what you're doing. So.
And just to add to that, one of the considerations is, of course, the element size. So the general element size we've used is 20 millimeters, and the height of this is roughly 2,500 millimeters. We already have 131,000 elements in here. So if you say wanted 3 or 4 elements through the thickness, then that is going to drive up the element count pretty
3, 4,
pretty
5, 6-fold. Yeah, it's going to be crazy.
So you have all of these different considerations, and it's always a trade-off.
Yep, there is always the trade-off. So what I like to do, right, is when I first start doing some simulations, some design validation of my particular design, go ahead and go with like maybe a more coarse element size to start out with, right? And just, run your analysis. And if you see what's expected, right, it's like, I'm gonna apply a load here. If there's a deformation in that area, sure, that's expected. But if there's a deformation somewhere completely different than what you expected to happen, then maybe start, driving the mesh finer and finer and figuring out exactly what's going on. You don't want to start running the most fine mesh possible. I made this mistake when I was learning all this stuff in college. I was like, oh, I'm just gonna skip all of these simulation iterations. I'm just gonna make 4 million elements, and I'm gonna run this thing for 15 hours, and hopefully I get the right answer. And we talked about this in a couple of AVAs ago, right? There's a stage in which increasing the amount of elements is not going to increase the validity of your results. You're going to hit this plateau, and increasing the elements, but beyond that are going to give you reducing gains, right? So what else do we got? Can you run internal expansion to compare the results as well? Because we did compression on this guy. So yeah, it's the same thing, right? You just apply the loads in the other place.
Different locations, yes.
Yeah.
So I'm going to get rid of those. Just apply loads there.
On the inside.
On the inside instead.
And same thing on the bottom.
Same thing on the bottom.
Yep, and you just run the same simulation, and you can look at it that way too.
Yeah.
So there's another one. Let's see here. Any other questions? Can you include welds in the analysis? Is that better than doing bonded connections?
No, it is not. I mean, you can include it. Yes, it's not better than doing bonded connection stuff, unless you are really specific about analyzing the welds. In which case, I would recommend analyzing them separately. Trying to combine welds, especially if you are expecting to model the weld beads as solid models, that doesn't usually doesn't end well. Usually is not a great idea because of I guess because of the type of behavior that weld beads themselves tend to exhibit. So if you have welded connections, as much as possible, please try and use bonded connections to replace them. And if you did really want to look at the validity and the strength of welded connections, then, like I said, reach out to us, and we'll give you some best practices for that, because it's a different approach for sure.
Yeah, and remember too, like when you're looking at simulation as a whole, that's pretty cool. When you're looking at simulation as a whole, it's not exploding. That's an exaggeration of the deformation. Just FYI, everyone.
That's the actual deformation.
When you're looking at simulation as a whole, during the design process, right, you're not trying to get exact answers. It's not a complete replacement for, real life tests sometimes.
Yeah.
You just want you're trying to validate the design to reflect the kind of results you're expecting. You just want to make sure that you're moving in the right direction in regards to your design, not necessarily being like, hey, this design's I'm going to run into 0.726 millimeters of displacement at this point. And that's exactly correct. Remember, like, it's not going to be completely the same, right? There's things like when you're looking at materials as a whole too, when you're looking at a lot of these alloys, it's probably not uniform.
Mm-hmm.
Just gonna put that out there. Is material properties of the particular steel you're using aren't going to be exact the entire width of the section. So just a couple of things to note there. What else? Let's see what we got here.
Oh, and by the way, this is the internal pressure results.
Yeah, so it's pretty close, I think.
Yeah.
Well, no, the displacement is going to be different because the force is coming from a different direction.
It's coming from a different direction.
If we look at the stresses.
Stresses will be about 6,000.
Let's see what else. What else is in 2019.1?
2019.1, you have a couple of other things. You have a bend constraint that you can now use directly. You can apply it to surfaces, and you can do a couple of different things with it. You also have, there's one other thing. Fatigue. When you're running a fatigue analysis, you have a signed and an unsigned result. So a stress result. So it gives you signed stress and unsigned stress. So it gives you positive or negative, which is useful.
And then another question here. How do you export SSL results? SSL results.
Is that the inventor stress? No, I think.
Yeah, can you expand on that a little bit, Sasha?
Yeah. Yeah, so earlier, by the way, the stresses that we had was 6,063, if I remember correctly.
Yeah, and we're at
5,700, 5,800.
So it's pretty close.
Close enough.
Oh, the stress linearization results without Excel. You can export to a CSV. You don't need Excel to open it.
Yeah, you can export these results to a CSV.
Yeah, which is what Nikhil did. If you don't have Excel, how do you do that? I don't know. Can you generate a CSV without Excel? I don't think you can.
I think you can generate one, right?
I'm not 100% sure. Inventor might install that for you, that thing that it needs to export the CSV.
Yeah.
You can't open it.
It's an interesting question. I don't think I've ever thought about that.
Yeah, I've never had a computer without Excel that I've used like I've needed to like export stuff on. I think like the same question probably arises for bill of materials and stuff too. I can look into that. Yeah, without Excel.
That's interesting.
Huh. Let's see. More information on analyzing weldments. Is there a way to analyze a different type of welds? So welds is another, animal entirely. You don't analyze welds as welds. I was talking to Nikhil about this when Nikhil started here. Maybe it was almost a year ago now. Is the way you analyze welds? Yeah. So yeah, the way you analyze welds is different, right? You imagine them as other things, or you use like line elements. Is line elements? Line elements for welds as well. So it's a little interesting when you're looking at welds. You want to be able to represent them as something that's close to them, but not actually represent them as welds per se. So
typically it actually makes sense to use a combination of line elements and shell elements as opposed to solid modeling a weld. It's interesting. It's something that takes some explanation before you can wrap your head around it. And that's exactly why we said, if you have questions on welds, feel free to contact us, because it's a completely different sort of workflow.
Yep. And the last question here. How do you define the perpendicular direction if you do not have half the model with a symmetry constraint? Perpendicular direction.
Oh, so
when you're looking at this,
that's if you didn't have half the model. That's a good question, actually. You can
do a section
view.
Yeah.
So section. Make sure if you do a section view, this is the default option, by the way. You're not going to see anything. You will have to select this option, section with the cut solid, and then you can drag that to a location.
And then do it that way. Yeah, and then once you get that section view, you can select something on the inside of the surface and something on the outside of the surface.
Yeah.
And then you have information.
But it's easier, one, to do the section view. That's the next step. And also, secondly, if you do have a whole model, you're spending more time running it anyway. So it may make sense to just start off with a half section or a quarter section, if that's an option.
Yeah, think about it, right? Is if you have the whole model here, you're not using half of it, your element size is going to double, approximately double.
Or quadruple if you can use a quarter section.
Exactly. Or more than that, right? Depending on if you're doing like domes and stuff. If you're doing domes and stuff, you could like make it so small, it's cool. Anyways, beyond that, yeah, so you're going to start increasing the amount of nodes, the amount of elements. It's going to have to calculate a lot more stuff, and then you can hear your computer chug for hours, possibly depending on your mesh sizing. That's a great question. So, let's see what else we got. I think that's just about all of the questions that we have for today. I'll give everyone another 30 seconds or so to ask some. I'll make a couple of announcements. So next week's AVA is going to be about iLogic, kind of how to get started in iLogic. It's been a hot topic. I'm not even as of late, but as of like the last year, maybe almost 2 years, right? A lot of people have started looking into design automation as a whole, to be able to reduce that design process time, and to get a bunch of stuff out the door faster than normal, especially if there's a lot of repetition involved. I know Nikhil's been working on some projects for a couple of customers as well, for some of that iLogic stuff. But Eric Paul, who actually shares an office with myself, is going to be teaching people, not people specifically, specifically you guys, the viewers, how to get started using iLogic, what kind of resources to use, and how to get familiarized with the iLogic browser in Inventor. I know it's, when you're looking at design automation, automatically people think of coding and you have to be like some kind of computer science person to do it. It's a lot easier than that. It's only like if-then statements. It's, the for loops aren't very complex. You don't have to know a programming language to do so. Inventor helps a lot in that regard. So we're going to go over that next week. So make sure you attend if that's something that definitely interests you. And a question about, let me pull this up. Sasha has a question about converged results. Go ahead and type that question in, Sasha. We'll make sure to take care of it. So yeah, be there next week for that if you want to learn more about iLogic, and how you can get products out the door faster. So we'll wait here for Sasha's question real quick. Let's see. Yeah, anything here yet, Sasha? Looks like maybe you haven't typed in the question yet. Anything else to add while we're waiting for this question to kill?
Don't believe so.
Yeah, nothing particular about stress linearization, but like just random best practices in regards to simulation.
For those of you that have used stress linearization in simulation mechanical before this, the interface is going to be very similar, as you could probably
It's
tell.
probably almost exactly the same.
Yeah, it's pretty much the same concept, the same nomenclature and everything. So that should be fairly familiar to some mechanical users.
Yeah. All right. Here's a great question. How sure are we about results without a converged study? Results without convergence? You can't be sure because the results didn't converge necessarily. It depends.
It depends. I mean, there are some problems that you expect to not converge.
Yeah.
You would validate them using essentially using results, because you need something to be able to verify.
That's
right?
It's
a very specific case.
Yeah, and I think those kinds of simulations where you expect it to not converge aren't super common when validating designs with loads and stuff on them, right?
Yeah.
You expect it to break at some point or to deform beyond whatever. So if you are getting results that don't converge, go ahead and check. Well, the first thing I would do is I would run a normal frequency on the entire thing. If you run normal frequencies on your particular part, you'll figure out what's happening. You'll get like a super exaggerated version of what's supposed to happen. And if it's like not expected, then maybe look at things like your loads and your constraints. It's almost always constraints.
Almost always constraints, yeah.
Yeah, so that's just one thing to do. So if you want to talk about that deeper, Sasha, let us know. Just send us an email, and we can talk about it. Figure out, if that's something that's happening to you, let us know. We can take a look possibly.
Yeah, and typically, if you're not reaching convergence or not getting to convergence, you're probably running a nonlinear analysis. And if you're running a nonlinear, then you should be able to play with the convergence parameters as well.
Yeah. So that's another thing too. But run normal modes on that and see if you get some weird natural frequency stuff happening and possible explosion of like parts. So let us know. All right, cool. I think that's it for questions. Thanks again, everybody, for joining us today. Thanks, Nikhil, for being here today. Talk about stress linearization. I know when you heard it was in Nastran, you were like, hey, let's talk about this. This is important. And it is one of those things that was in simulation mechanical that people have been waiting for to show up in In-CAD. So thank Autodesk for putting that in there for us.
Yep.
With that, I think that should be it for everything today. We'll see you again next week, everyone next time. Same time, same place, Thursday morning at 10 for iLogic 101 next week. So thanks, everybody, for attending, and we'll see you then.
Thanks,
Bye-bye.
everyone.